thank you very much for giving us of your time, all of your efforts and research and sharing with us today about planets in general. Can we live on another planet? And all of your research involving planets and the necessary conditions of life. So here is a little bit of a background about Dr. Shkolnik. She's a professor of astrophysics at the School of Earth and Space Exploration at Arizona State University. She's also an expert on exoplanets and stars, including the sun. She studies stellar activity and star-planet interactions using telescopes on the ground and in space to answer questions involving stellar evolution and planetary habitability. And she continues to execute new observations with existing telescopes, both on the ground and in space. And she's also now designing new small space telescopes dedicated to these experiments. So I am going to let Dr. Shkolnik explain more about her research and, of course, today's topic, which I know many of you are very interested in, as I am. So thank you. I'm going to turn the mic over to you.
Okay, well, thank you so much for that introduction and for the invitation. I so enjoy speaking with all of you. Let me start sharing, but in principle, let me just get this first slide up and you can tell me if it's all working as it should be. Let's see. So you guys see my slide?
Yes, but do you want to do it in presentation mode? There you go. Perfect.
There you go. Yep. It just took a second. Thanks. So as Rabbi Levertov said, I study exoplanets and stars. Exoplanets are the catch-all name of planets outside of our solar system. So we have many known solar systems now, and we will go over, I'll show you some of the evidence for it and how we discover them, and then talk a little bit about planet habitability, but I'm going to focus primarily on Proxima b. Now, I don't know if anyone knows what Proxima Centauri is. If you want to nod your head, I can't see all of you now, but it's our very nearest stellar neighbor. So the closest star to the Earth is, of course, the sun, but the closest star to our solar system is Proxima Centauri, and it is now known to have its own Earth kind of, or Earth size, Earth mass planet. And so I'm going to kind of just focus on that one and give you a broad overview of planets in general, but then focusing more on this one, because this one is so exciting because it's the one, because it's the closest exoplanet to our system, it's the one that people are now seriously thinking about ways of sending little cameras outside of our solar system to go take a picture of it. So a lot of this is just very, very exciting new research. So we can get started. Let's see. So the study of exoplanets, of course, in a philosophical way, I'm just going to turn off one second my meeting controls. There you go. The in a philosophical way has been going on for hundreds of years, and maybe even longer. But here's just one very early example by Giordano Bruno, who said, 400 years ago, innumerable suns exist, innumerable Earths revolve about these suns, and living beings inhabit these worlds. So the idea of planets with life outside of Earth is something that people have been thinking about, but was really only until very recently become part of the scientific pursuit. It has been a philosophical pursuit for hundreds of years, but only in the last 30 years has this become a real scientific effort that is truly funded by both private and public entities like NASA, the Canadian Space Agency, the European Space Agency, and so on. And I was fortunate enough to be an undergraduate student in physics up in Canada, in Nova Scotia, when the first exoplanets were being confirmed. And that was really the pivotal point in my own personal career of of going from a physics laboratory into astrophysics when I first learned about these exoplanets. So here is a histogram just showing you the summary of all our discoveries so far. So we have year on the bottom, on the x-axis, hopefully you can see my mouse, and the number of planets discovered each year on the y-axis. And the color coding here is different detection methods. And I will show you how we actually find these planets. And I will focus on the two most popular ones, which is the radial velocity method and the transit method. But the biggest thing I want you to take out of this slide is that the very first planet that was discovered was in 1989. It was really 1988, and then published in 1989. And only since then, we have been increasing our number of known planets. And as of today, we have well over 4,000 confirmed planets in our galaxy, which I think is pretty remarkable, and all very, very new. As you can see, most of this work was just done in the last 5 or 6 years, thanks to the Kepler space mission, which is a NASA-funded mission that stared at thousands of stars and discovered thousands of planets. And so to put it all into context, right, this is just an image of a galaxy that's very similar to our Milky Way galaxy. And our Earth and Sun and all the planets in our solar system are kind of here, about 2/3 of the way out from the center of the galaxy, right? And when you think about it, the galaxy is quite huge. It's 100,000 light years across. But in this little dot is where all those 4,000 exoplanets that were discovered, including the one around Proxima Centauri, which we call Proxima b. So what I wanted to say, that even though 4,000 seems like a lot of planets, it's really, we are really only probing a very, very tiny region of our galaxy. And so 4,000 is by far an underestimate of the number of planets in our galaxy. There are in fact billions and billions of planets in our galaxy, hundreds of billions of planets in our galaxy. Remarkable, don't you think? But of course, because we are also interested not just in the numbers of planets and in the diversity of planets, we're also interested in the habitability of planets. Could life as we know it exist on those planets? And one simple way that we try to at least identify a planet that might potentially be able to support life is to ask whether or not it is orbiting in the habitable zone of its star. And the habitable zone is this green ring in this cartoon. This is a cartoon of our solar system where the sun is in the center, and you have Mercury and Venus and Mars and Earth and Mars, and Earth is orbiting very much in the habitable zone, thankfully, as we are clearly comfortable in our existence here on Earth. But that's because at 1 astronomical unit, which is the distance between us and the sun, that is where our habitable zone is. However, if you have a star that is hotter than the sun, then you want your habitable zone to be further out, right? You don't want to be too close to the fire. If you're too close to the fire, your water will boil off, right? And you will not be able to sustain life. But if you're too far, it'll be too cold, and there'll be either no water or it'll be an ice giant of sorts. However, we have plenty of cooler stars and stars that are much cooler than the sun. So if the sun is, say, 6,000 degrees, cooler stars are about 3,000 or 4,000 degrees. And therefore, if you want to stay warm, you have to get closer in. And so those habitable zones are much, much closer to the sun. And the reason why I wanted to introduce that is because Proxima Centauri, this particular star that is going to be the focus of our search for life right now, is, or at least in this talk, is one of these cooler stars where the temperature is much smaller. It's about 3,000 Kelvin, half the temperature of the sun, which means that the habitable zone is much closer. Now, Rabbi Levertov, I can't see any chat questions if there are, so maybe you could monitor if there are any questions.
Okay, perfect. There's one question. How many suns with the 4,000 planets?
How many suns with it? Well, that's an excellent question, because some suns, some of these stars have 2, 3, 4, 5, 6, 7 planets like ours, right? So we have 8 planets. So there's 4,000 planets probably discovered around, let's call it 3,000 stars. So the current record holder is 7 planets in one stellar system. But yes, they do often have multiple planets around the same star. Sometimes because of our detection technique, we cannot discover all the planets around them, but for sure we know that some of them have multiple planets. Okay, thanks, Rabbi. Feel free to.
Okay, perfect.
Thanks. All right, let's go to where I was going. For some reason, I guess we're gonna watch the movie again. Okay, so Proxima Centauri is one of these cooler stars, also called an M dwarf. Now, I don't know why I can't switch. There we go. So because I don't have a ton of time, because as I said, I'm going to try and keep it to 20 minutes, but I did want to give you what I think are the 4 most important facts of 3 decades of planet hunting. Okay, this is my biased view, but I think that for those of us interested in understanding life outside of the Earth, this is what I think is the most important ones. So first of all, exoplanets are everywhere. I already mentioned to you that there should be billions of exoplanets, but in fact, when you extrapolate the statistics of these 4,000, we now know that there are in fact more planets than there are stars, and that on average, every star has a planet, right? This is total news, right? And I suspect many of you didn't know this. This has not even made it into the textbooks yet. Most astronomy textbooks have not yet caught up with this fact that on average, every star has a planet. They're extremely diverse. So these planets are very different from the planets in our solar system. And they, in fact, span a much wider range, right? We usually think that the planets in our solar system are very different from one another. They are. Jupiter, Saturn, Uranus, the Earth, Moon, they're all different. But there is even a wider range of diversity in these 4,000 exoplanets. At the moment, there are about 10 confirmed planets in the habitable zone, in that green ring I just showed you so far, and counting. A bunch of candidates, and people are following them up to confirm them. And 25% of planets around these low mass stars, these cool stars, right, are in fact in the habitable zone. So what that means is if you work out the math of the number of stars in our galaxy, the number of low mass stars in our galaxy, the number of those that have rocky planets, and the number of those that have rocky planets in the habitable zone, it turns out to be about 40 billion small planets in habitable zones around our galaxy, which is a surprise, I think, to some people, but also very exciting. So I hope that that bit of news is inspiring in some way, because what that's probably telling us is that life is probably ubiquitous in our galaxy. Some form of life. It may not be like us. It probably won't be like us. But life will have many opportunities to exist. So these small stars are not just cooler, but they're also smaller. So here's an image of our sun, which could be familiar to many of you. And a small star, these M dwarfs, are about half the size or smaller. And here's a plot showing you the distribution of different kinds of stars in our galaxy. We have mass on the x-axis here, and where 1 is the sun. So here we have the sun up here, where we've normalized everything to the sun, the same luminosity, the same brightness. And these low mass stars are down here. Look at that, on a log scale. For those of you who are familiar with log plots, this is an order of magnitude, a factor of 10 on each tick mark. And Proxima Centauri is down here, right down here, where it's only 0.2% the luminosity of the sun. And what that means is that that habitable zone, that green ring, must be very, very close in, right? And another important point that this diagram on the right here shows is that these low mass stars, in fact, dominate our galaxy. 75% of all the stars in our galaxy are these low mass stars. So stars like our sun, when we say that stars like our sun are normal or average, that is not the case, in fact. The sun is rarer than these low mass stars. Not so rare, but rarer. So let's talk a little bit about how we find these worlds. The transit method, I think, is pretty straightforward to think about. It's just a geometric effect. If you have a planet that cuts right across a star, right, the drop in light that you measure from the star tells you that the planet is there. very much like an eclipse, right? When you have a solar eclipse and the moon is coming in front of the sun and it becomes dark for a few minutes, this is exactly what's happening, but we measure little tiny drops. And this is the way, in fact, that the Kepler space mission did discover many of its planets, or all of its planets. That's called the transit method. And here's an example, another one you might have seen in the news recently from a few years ago, the transit of Mercury, where people were measuring the drop in flux from the sun because of Mercury cutting across the disk of the sun. And another exciting thing about these transiting planets is, in fact, currently our best way of measuring the composition of these planets. So if we're looking for water on these planets, it's because it's when they transit that you can then look at the chemical signatures of all the atmospheric molecules and constituents of the atmosphere. So that's another wonderful bonus of the transit method, is that we have, it's a very nice direct way to detect the chemical composition of these planetary atmospheres. And if you're looking for life on these planets, the best way right now that we know of how to do that is by analyzing the chemistry of the atmospheres, right? Is there oxygen? Is there methane? Is there ozone? Those kinds of things. The kinds of things that we find in our own atmosphere that are indicative of life on the surface. So the transit method, though, requires that you have a orbital plane directly aligned with our line of sight, right? So if it cuts right across, then we will see that the planet transits. However, only 2% of planets roughly do that, and 98% of the planets don't do that. They have orbits that are inclined relative to our line of sight, relative to our telescope's viewing angle. And so if you want to find many more of them, all these other 98% of the planets, you need a different method. And in fact, it was the first successful method, which is called the radial velocity method, also known as the Doppler method. And what happens here, what the cartoon is showing, is that the planet orbiting the star has enough of a gravitational pull on the star that we can measure that. We can measure the motion of the star as the planet yanks on it, right? Which is kind of remarkable that we have that kind of precision. And we do that using spectroscopy, where we break up the light from the central star. We look at the lines, these characteristic black lines are absorption features from elements in the stellar atmosphere. But by looking at those lines move back and forth, we are measuring the motion of the star. But if the star is alone, those lines wouldn't move. It only moves because there's a massive body, which we can measure its mass, a planet that is tugging on it. It's really quite remarkable. And the precision with which we are able to measure this is now about 20 centimeters per second. So like this much per second. So imagine a star as big as our sun, right? And we could watch it do, I can't, usually if I'm on stage, I will walk at this pace for you, but on Zoom, it's really hard to walk at this pace, but 20 centimeters per second is like 1, 2, 3, 4, like it's very, very slow, like turtle speed. But that is the precision with which we can measure the speed that stars move back and forth. And it just makes astrophysics and astrophysical instruments supremely impressive. I'm still in awe of all of this, even though I do this all the time. So that was the technique, actually. It was that radial velocity technique that discovered Proxima Centauri b. And it was this whole program called the Pale Red Dot, where people were looking using the small ground-based telescope here in Chile. They're looking for planets around our nearest neighbors, Alpha Centauri A, Alpha Centauri b, and this is Proxima. This is just a cartoon of it, but you can see that it's all part of the same stellar system. There's a lot of effort to understand planets around these systems because they are our closest systems, as I said. They're only about 4 light years from us. And so a light year is the time that it takes light, is the distance that it takes light to travel in a year. So that's really far. But when I told you earlier that the entire galaxy is 100,000 light years apart away and our nearest stellar system is 4 light years, it's really like right next door in comparison. So that's just showing you where Proxima is. And this is just a beautiful time lapse showing you the Milky Way of the telescope that discovered Proxima b. And the signal, the Doppler signal, that radial velocity signal, is only 1.4 meters per second. So just imagine you're walking. It's like a normal 1 meter per second kind of pace. And that is the precision, that is the little tug that this tiny little planet has on its star that we've been able to measure. And the orbital period, which is its year, is only 11.2 days. So it takes 11 days to go around its star once. And yet it is in the habitable zone. We take 365 days, right, to get around our sun. But Proxima b, that planet, takes only 11 days and is still in the habitable zone. Why? Because, as I said, Proxima Centauri itself is a very small star and a very cool star. And so if you want to be if that planet wants to be habitable, it has to be really close in. And so its year is only 11 days, which is remarkable. All right, so the question then, of course, is it habitable, right? It is in the habitable zone. I already told you that, but it doesn't necessarily mean that it's habitable. In fact, habitability depends on many more things than just being in that green habitable zone. It depends on the star's properties and, of course, on the planet's properties. And here's just a few things for you to read over and mull over of all the different things that we, both in astrophysicists, but also geophysicists and chemists and atmospheric scientists and environmentalists and all sorts of people are working on this question, not just for Proxima b, but for the 40 billion habitable zone planets that we know are out there. And so we're trying to understand all these things. I specifically focus on the stellar properties primarily. I work on this realm, and then there's other groups of geophysicists who work, and atmospheric scientists who work on the planets. And together we're going to be bridging the probability of habitability of these planets. Another part of my work, those small satellites that Rabbi Levertov mentioned in my introduction that I'm working on is to try and measure flares on these stars, because the flares dramatically alter the atmosphere of the planet. So you could have a perfectly wonderful Earth-size, Earth-mass planet in the habitable zone, but if the star is doing this, which is an actual movie of our sun, so the sun actually does, this is a real movie of a flare on our sun. And some of these low-mass stars do this every day and with much more powerful energy. So if you have a planet like Proxima b, very, very close to its star now, remember, it's only at 5% the distance of the Earth and the sun, and the star does this every day, the planet may be in the habitable zone, but its atmosphere may have been completely stripped away billions of years ago, right? It just may not have an atmosphere anymore. It might just be a barren rock, but we don't know that yet. So a lot of my work is trying to figure this particular question out. How do the stars behave and what is the effect on the planet atmosphere? And so it's this interaction, the star and the planet. And another part of my research is to study the planet's magnetic fields, because we think that the Earth's magnetic field does a lot of work to protect our atmosphere. So this might be a yet another necessary condition for life. So I guess the answer to the question, is Proxima b, the planet around Proxima Centauri, habitable? I think the answer right now is it's complicated and we don't know. But we are working hard to be able to answer this. And so the very last thing I wanted to leave you with some imaginative work, it's ongoing, but it hasn't happened yet, is how can we reach Proxima b? And one of the efforts going on right now in order to get there and not yet send humans or anything out there, I think that our first attempt will be to send little tiny cameras about the size of your fingernail that will be accelerated through lasers on Earth. And it could take, if we could accelerate it to about 20% the speed of light. Remember, it takes 4 years for light to travel to Proxima Centauri, or for us to receive light from Proxima Centauri. So to actually send an object will take many, many more years. But if you can accelerate it to a significant fraction of the speed of light, it could take only 20 years to get there. It could take its observations, and then it would take only 4 years for the images to come back. So there's a lot of effort being put into this particular thing, and some of us at Arizona State University are also working on this big question. So the last thing I want to leave you with is this diagram here, just to inspire you that the next time you look up in the night sky and you see all those beautiful stars, that they're not just stars, that they're solar systems, that almost all those stars that you see probably have planets around them. And it's just a matter of understanding them better. So that's it. That's my talk. I'm happy to take any questions.
So would you like, first of all, thank you. I think it's awesome. I thought that your last question should have been before, are they habitable? It's, can we get there?
Can we get there?
Meaning, can we make it to such a planet?
Well, I think, this is what people are trying to figure out, but at the moment, we don't have a way or any ideas how to actually get humans there. I mean, if you think about it, it takes 4 years for light to get there. The best estimates at the moment is it would take 800 years for a spaceship to get there or so. So there are, as you can imagine, challenges to getting.
You need to have families on there.
What's that?
You need to have families on the spaceship.
You need to have families. Yeah, you need to build some sort of giant spaceship that could maneuver itself and hold on to all these people, and then have life, humans procreate on it. It sounds, I would say, way more complicated than just getting to the moon, which we're still trying to redo and then go to Mars, which is also its own challenge. And Mars is really just over there in comparison. So let's first get humans to Mars, back to the moon, then to Mars, and then maybe we'll have some better ideas of how to get to Proxima b. But for now, I'd be delighted, just for the little camera, right?
Yeah. So the research on that is actually quite difficult because of that inability to really be there.
The research on, you mean sending these little cameras?
Yeah, or even studying Proxima b in general.
Well, we do things remotely. So we have telescopes on the ground, and we have telescopes in space that study the star. And so we can learn a lot about the planet by understanding its star. We know the planet is there because of its gravitational pull on the star. So we know pretty much the mass, and we know its period, which means we know its temperature, because we also know the star's temperature. And we have a program actually with the Hubble Space Telescope to look at the stars flaring. Like I was showing you all these flares, and we want to understand the flaring. So we just finished up a program with Hubble to look at the flaring of Proxima, the star. And then we can apply computer models onto what must be happening to its atmosphere. So we're actually learning a lot from remote observations. I don't think you have to go there to necessarily to get.
Right, I don't mean literally physically, but something that's pretty amazing though. I love this. You have a couple questions on the chat. Should I read them, or do you want to just?
Let me I'll see the chat as soon as I stop screen sharing. Then I can see the chat.
It's all from
Judy.
Yeah, from Judy.
Thank you, Judy. Why do you think it is unlikely that human-like life exists on these planets? So I did say it was unlikely. I mean, I really have no idea. There's no statistics to tell me one way or the other. It's just there's so many different kinds of life on Earth that different kinds of life could exist elsewhere, even other ones. These other kinds of life that are even more varied than the kind of life we have here on Earth, especially if conditions are not exactly the same. If you have a planet that is a little bit heavier, right, than Earth, then you might not have as tall of creatures, for instance, because the gravity will be heavier on a heavier planet. And so we might have flatter people or flatter animals or things that just crawl on the ground or just little microbes. It just may never get 6 foot tall creatures. So who knows? I mean, the diversity of these planets is so wide and so huge that I don't expect necessarily to have life just as we know it on all of them. What kinds of life and planets do you expect? Animals, I just answered that a little bit. Again, you know, it's really, really hard to know. Why there's a big question right now is how do we discover life as we don't know it? That is a huge, I wouldn't say it's a huge, I mean, there are people who are working on it, and that line of reasoning is now growing, but it's a huge question. And more people are starting to ask and try and figure out, how do we look for life that we don't know? So right now, a lot of the focus has been on life as we know it, because at least we can identify something. We know how humans affect our atmosphere. But life as we don't know it is harder, but not impossible. And some very clever people are trying to work that out. Are there 4 seasons during those 11 days? It's a good question. So there would be 4 seasons if the planet was inclined, if it had an inclination on its axis. So our seasons of winter, say, and summer, say this is the axis of the Earth. I have no props at home here. I have to find one of my kids' balls. But if you have the axis tilted, right, then in a certain part of the year you have winter in the north, right, or summer in the north and winter in the south, if the sun is here, and then it goes this way. So if Proxima b, the planet, is inclined, it would have seasons in its 11-day year. Whether or not it's inclined, though, we don't know yet. So I don't have an answer to whether that would happen, but it definitely could. Are there any astrophysicists that believe human life exists in our galaxy? I think most astrophysicists would tell you that there's probably life elsewhere. Whether it's anything like humans, I don't know. My opinion is that it's probably unlike humans, just by the virtue of the diversity of the planets, but I cannot speak for other people. If we go to Mars, is it possible to bring back an unknown virus like COVID-19? Interesting question, Alan. I think probably not. First of all, there are huge, first of all, I don't know if viruses exist on Mars. There's no evidence of viruses on Mars that we would.
Can I jump in? What about bacteria then?
Or bacteria? There's no evidence of bacteria on Mars either.
Oh, okay, okay.
But whatever bacteria there is on Mars is because we brought it there with our own rovers. If it has its own bacteria, we don't know about it. But even if we were to bring something back, there are many policies in place to do what we call planet protection. So we do our best to not send microbes to Mars from Earth, but equally so, if we were to bring something back, I'm sure it would be isolated in such a way that we would want to study what came back from Mars without contaminating it. So I think that it's actually a very small chance that we would be contaminating ourselves with things that we brought back.
You have a couple mics that have been unmuted. Sheldon, did you have a question?
Yes, I just have a question that, do any of these explorations have any effect on our atmosphere on Earth? Anything we're sending out there, could that affect our atmosphere? And how?
Our own atmosphere. Do you mean like satellites affecting our own atmosphere?
Well, anything that would maybe affect the rainforest or affect our temperature on Earth, or do any damage to Earth?
The first thing that comes to mind is what we call space debris. And so right now we're sending lots of satellites up there, most of which have nothing to do with astrophysics, right? These are Earth observing satellites or communication satellites. These are satellites that in principle are for us here on Earth and have nothing to do with astrophysics. We're looking for those. We have some space telescopes in there, but those are very few compared to all the other many thousands of satellites up there. There is concern of space debris. So when these satellites stop working, it's just junk, space junk floating around. And many of them do have to degrade in the Earth's orbit. So there is concern that if we start populating the orbits all around the Earth, and many of these satellites start degrading, that we could be polluting our own atmosphere through the through the fact that the satellites burn up in our own atmosphere. I don't think we're there yet, that it's actually affecting our atmosphere in any way or affecting Earth's temperature in any way. But it is something that people are keeping an eye on so that it does not happen.
Okay, thank you.
Stevie, you had a question?
Yeah, why don't we try to go to Venus instead of Mars or Mercury? You know, I mean, it's closest to us.
That's such an excellent question. And there's many scientists who are advocating that we send instruments and satellites to Venus because it's a very interesting planet. Sending humans to Venus is not something people are really advocating on. It has a very thick CO2 atmosphere, and it's much, much hotter because it's closer to the sun. So sending humans there is not something people are all that excited about, especially because the moon is very close and a bit more straightforward, and we've done it before. And Mars is very exciting for exploration because it has, and people want to understand habitability, and there is some thought that Mars might have been habitable in its past. So it's a way of learning. And so I think between the heat and the thick atmosphere of Venus, it's not very hospitable to put any humans on. But from a scientific perspective, it's very exciting because we want to learn why a planet that is not so different in mass than the Earth, right? Not so far off, has such a completely different evolutionary history. Like Venus right now is in no way habitable, as I said, or hospitable to life. And yet Earth is so spectacular and gorgeous, and it's a paradise for us, right? So yes, I think scientists would love to go to Venus and have more missions. And there's a whole group of planetary science who are advocating that NASA fund, $1 billion mission to go to Venus. So hopefully, I think, you won't be surprised. I mean, you might be surprised to hear that probably within the next few years, I expect that someone will have won and had put a concept into NASA and will have won a mission to go to Venus, and we'll learn so much more about it.
Thank
So
you.
before you ask your question, why can it be done without NASA?
Well, right now it's very expensive. It doesn't require NASA. But if you say you want to have a $3-4 billion mission, at the moment, most philanthropists have not been spending that much money. But as you see, things are changing, right? SpaceX, for instance, right, is definitely changing the game. Where they just, privately launched 2 astronauts to the International Space Station, and that's a first to have commercial flights like that to the space station. So I think you're right, Rabbi. I think that if you have the will and a few extra $1 billion to spare, and there are people like that, right? Right, there are people who are privately funding a lot of space exploration, and I think that would be spectacular to have more of that.
Got you. Okay, Stan, you had a question.
Yeah, you're speaking about life based on our atmosphere, oxygen, and that type of thing. What if you had a planet out there where people were breathing nitrogen to survive, and that type of thing? Is that a possibility? I mean, if we're basing it on what we know, not what could be 800 years away. So I'm just curious if that's a possibility that anybody is looking at or not really. You mentioned peripherally that was a possibility. But.
Right. I mean, yes, I think it's a possibility. It's that we just don't know how they do it or how they interact with our atmospheres. So right now, the way we can telescopically observe the planets for habitability, or whether it's inhabited, is by the chemistry of their atmospheres, right? We're not able yet to look at a planet and see roadways, right? Or intelligent life infrastructure and things like that. So we just aren't capable of doing that. So life as we don't know it, as you suggest, I'm sure is out there. We just don't know how to find it yet. However, this is where SETI, the search for extraterrestrial intelligence, I find so exciting, is because in that regard, it does not require necessarily a life as we know it component as we do for the current molecules that we look for in biosignatures and atmospheres. There, potentially, and there has been no signal that I know of ever detected, but if there were an intelligent signal, then life as we don't know it, as long as it had some intelligence that we were able to decipher, would be a mechanism by which life as we don't know it could be discovered.
Thank you.
Sure.
I have a question. The planets in our own solar system are very far apart. How are we able to determine the makeup, the temperature, the volcanoes, and et cetera on each planet? We've obviously not been there.
Right. It's amazing. It's what we call remote sensing in many ways. So for instance, we have telescopes and we can take images in our own solar system. Well, even by yourself, you can look at the moon, right? Your eyes are like little telescopes. You look at light that's reflected, sunlight reflected off the moon hits your eye, and you can make some inferences, right? You can see the phases of the moon. So you learn that it's spherical, right? By seeing the crescent, you know that it's a sphere. By seeing the dark patches, you know that there's some difference in the surface compositions, because some are light and some are dark, right? I mean, even you alone can do that. And so we do that just with very sophisticated telescopes that our human eyes cannot be sensitive to. And we look at different wavelengths, and sometimes we can, like if it's in our own solar system, we can send a rover onto Mars, right? So now we have like a little car on Mars, and it takes its own chemistry. It looks at the soil, or it digs a hole, or it takes pictures. So it's all about the technology and the constant evolving technology and the creativity and ingenuity of humans. It's all us, right? It's all of us and the generations before us who have been building this technological and scientific knowledge that allows for all these discoveries.
But a telescope can't detect the temperature on any given planet, can it? Or
yes,
the chemical makeup?
Oh, it can. Oh, it can. Okay. There's actually many ways we can do it, but I'll give you a couple of ways. Thermal, if you have nighttime goggles and you see the thermal emission, that tells you the temperature of something. And so we have built telescopes that are, say, in the infrared, and we have detected planets both in the solar system and out that essentially is looking at the thermal emission. How hot is this planet? And you can measure it quite directly. So that's just one way, but there's actually many ways.
Thank you.
Sure.
So question from Facebook, and I'm not sure, I messaged her back, but she didn't reply. But this was the question: what about non-carbon based life?
That's sort of what Stan was saying, some life that as we don't know it. Certainly that's a possibility. We just don't know exactly how to find it yet. But people are thinking about it. People are thinking about clever ways, clever chemical pathways where even life as we don't know it might indicate, might be detectable through its atmosphere. So it's a very active research program right now for several people, is to figure out life as we don't know it.
There's some underwater studies going on near volcanoes that show some things that look like they might be life that are not carbon based. But there's not a lot of work been done on that makes any accurate statements. I was wondering whether you'd heard anything much more about that. I stopped reading that stuff a while ago.
No, I don't know much about that. Do you know what they are? If they're not carbon based, are they?
I really don't know. A lot of this stuff, if you'll pardon the expression, a lot of stuff that's written is not true. So it's very difficult to evaluate statements made by individuals that you don't know.
Yeah.
Areas that you're perhaps not that sharp in. They can come up with all kinds of nonsense. And I did a fair amount of chemistry, and it's not unusual or unreasonable for some things to be not carbon based. And what they're using as a basis is nearby heat sources, like volcanic heat sources, way down below the ocean, where the temperatures and pressures are considerably different than anything above the ground. So you don't know what the heck is down there. And a lot of the stuff that's being stated, you don't know if they took a sample or they're just lying. It's very difficult to tell.
I do agree. I do agree with your earlier statement that you have to be careful what you read and make sure it's coming from reputable sources, especially if it's in the news.
You know, it's sort of funny. Those of us who are old used to be reputable sources, but in this particular area, I don't know any.
Well, you have Dr. Shkolnik now. No?
Any more questions?
Yeah, did anyone have any questions on this subject or maybe something else that she might have mentioned? I see Sheldon, you just unmuted.
Yes, I just have a question. Obviously, you're a brilliant scientist, and we appreciate your presentation, but over the last at least 3 months, we've proven that we can't even take care of our own planet with the COVID-19 and pandemic and everything else. Do you think more should go into that than space exploration?
Such a good question.
We can't, there's environmental issues there. We can't get along with people. People on Earth can't get along. I think it's more, to me, it appears to be more important to resolve our issues here on Earth before we destroy it.
I love this question too, by the way. Can you give the Torah answer as well?
You can give the Torah
You can
answer.
give us
I want to
a-
hear what the scientist says. So it's
Okay,
a great
well-
question.
Okay, well, I'm curious. I'll give you my answer, and then Rabbi, I'm curious to hear your answer. So my answer is, there's a few different aspects of it. One is, yes, right now we're in the middle of a pandemic and a crisis, several crises going on at the same time, and certainly they need attention. And doing space exploration is, in some people's view, a privilege and a luxury that our society has. I don't totally disagree with it, but I do also think about it as being the human imperative that some fraction of society will always want to explore, right? There's always people who want to take the boat offshore and see what's going on over there. So I'm not advocating that every human needs to become an astrophysicist and ignore all the other things going on the Earth, right? A subset of us focus on this, and you have your specialty, and the rabbi has his specialty and his mission on this planet, and so on, right? So everyone, there's a diversification of thought that is really necessary. One thing that I noticed in the last weeks when SpaceX did launch those 2 astronauts to the International Space Station, it was very exciting. 3 million people tuned into just to their YouTube channel. And because it was Shabbat, I actually couldn't. So I only heard that number after the fact, and it probably grew many times over since I heard that number of people rewatching the video. So it's inspiring, like anything that one should take. One should find inspiration in many places. And one thing that astrophysics has and space exploration has is an exciting and inspiring gateway into science. Now science, so you have this inspiration to science, then you have people who are excited about science and technology. And then many of those people then grow up to become biologists and medical doctors and chemists that do work on more earthly things. But if you ask many, many scientists how they got excited about science, a lot of them will tell you it's all about astronomy. So that's another thing. And then my last comment, I have, of course, many, many thoughts on this, but I want to hear what the rabbi has to say. My last comment is, it is not true that we are spending billions of dollars on space exploration in equipment. So we're not sending $1 billion into space. It's not like we stuff a rocket with $1 billion, right? That money is going to people's salaries. So in fact, the fact that most of that money goes to the economy directly into jobs, into technical jobs, interesting jobs, inspiring jobs, makes it all completely as worthwhile as any other job creator. you can have, right? The actual aluminum or the actual metal that the rocket is made from is pennies compared to the salaries of the people who have to invent them and build them and launch them, right?
It's good.
Good
Stan,
point.
you want to add to that?
I had a comment. I had a friend who was with NASA for 30 some odd years, and he said certain people get involved with applied science, and he was more involved with basic science, so that you don't know where it was going to go, but it wasn't to solve a particular problem. And I think it's a different, there are two approaches. It's not that one is right and one is wrong. It depends on where your mind is at that point.
And both are necessary, but the applied science doesn't work without the fundamental science.
Right.
If you don't have the fundamental physics or the fundamental anything, it can never, there's nothing to be applied.
That's why he was in basic, that's why he was in basic science.
As I am, that's right.
Stevie, did you want to add something to that?
No, I have another question, so I want to hear what you had to say.
Well, I was going to say, actually, Lou just added something to the comments that I wanted to include in that, but to sort of bring this into current events, there was a young kid who tweeted something on Twitter on Saturday when the two astronauts went in space. Said, "Great idea." I don't have his exact word, but it's like, this is a guy who was a nobody. He said, like, smart idea, just run away from here because it's all the craziness going on in this world isn't happening in space. So smart, to go into space and just escape it all. But I think that in Judaism, first of all, Judaism is not against space exploration. And I like what Lou added, which was we've learned so much for ourselves because people have gone and studied what is beyond us. And then there's this Jewish aspect that says if you want to appreciate God, you have to look sort of above. You can't just look at the picture. You got to look above the picture. There's a lot to be learned in our Jewish perspective when you have a bigger picture. The world is not just about me. It's not just about our city. So there is a lot of important life lessons that you take from all of that exploration. So that's just another aspect to it. And lastly, I think that one of the most important mandates in Judaism, which we always use the words incorrectly, and we always hear tikkun olam, which we think of as cleaning beaches and fixing different, building houses for people who don't have it. But really that's part of a greater, I chose two, by the way. I mean, you see that for so many things, those words are always used. But really tikkun olam is from a greater verse, which is that we should establish this world with God's kingship. In other words, this is our mission in life, find the godliness within everything. So it's not only in our little bubble, but in a greater aspect, when you find God, and finding God doesn't mean you all of a sudden see the light, but it means that you bring that, all of the lessons that we learn from the Torah, whether it's kindness, whether it's empathy, whether it's charity, the Torah is all encompassing. Find that in every aspect of our lives and every aspect of this world. And why would that exclude something else in the sense of space, planets, and exploration? So, if you want to tell somebody how they should spend their money, that's a totally different conversation. But is it wrong for someone who wants to spend their money in that way? Definitely not. I mean, if they've taken care of their obligations that the Torah tasked them with, which is 10% for charity, and if they want to give 20%, good for them, and they have a lot extra, I think Dr. Shkolnik mentioned $3 to $4 billion to send something to space. If a guy has 60 billion, why are we telling him where he should put his money as long as he's taking care of his charity obligation?
Rabbi, I think Sheldon's point is extremely important for everyone, not just the wealthy people, is because NASA is publicly funded. We are all paying for it, right? You're paying for it with your taxes. So.
Well, I'm very happy that I've invested in space exploration. Now I feel like I'm an investor. Thank you.
But just to give you one little statistic to make you all feel better about your tax dollars is that most of it is not going to NASA. And it's
I like how you mentioned it's salaries.
It's mostly salaries, but I will just say, just even from it's a pittance of how much of your tax dollars goes to NASA. The astrophysics budget is in fact not big at all compared to the rest of the government budget, and it's only equal to roughly, I don't know, a few dollars, $4 or $5 per taxpayer, or less. I don't know the exact numbers, but it's really nothing.
I see this question comes up apparently often for you.
If it comes out, if they spend 10 cents and we have spent 1/1,000,000th of a cent, it's a waste. Okay. I've been getting this waste for many, many more years than you've been alive. Everything I've ever worked on has always been not important until it happens. And it takes a little bit more effort to make things happen, as you're aware. So while you're making it happen, you're wasting money. What in the heck are you doing? And suddenly they say, my goodness gracious, we can do that. I wonder how that happened. And
Right.
the reason why it happened is because folks like you, and perhaps sometimes me, made it happen with a couple of cents that they didn't want to spend at the time. It's unfortunate, but that's the way it is.
Yep. But now I feel very good now that I'm an investor. Stevie, you had a question?
Yeah, I did. Do you think that we will be able to set up a space station on the moon, and what value would it have?
Space station on the moon, what value would it have? I think we will be able to do it. I think the government is actively trying to do it. I think there's probably lots of value. One way is it's going to be training us on how to build a station on Mars. So it's a much easier place for us. It's just, we're very close. You can go back and forth relatively quickly. We can also put more technology on the moon. I, for one, from an astrophysics standpoint, would love to see more telescopes on the moon. The moon is the Earth's atmosphere is really quite challenging for us to do many observations. So putting more telescopes on the moon at different wavelengths that we cannot observe from the ground here on Earth would be very beneficial to science. I know that NASA has its own plans for technology development on the moon, and I'm sure there's also political interest there as well that I do not get involved with too much myself. So,
Thank you.
Sure.
So is there any last questions before we, Ethel, you have a question?
It's not really a question, but there are a lot of benefits from the research. Like we had to develop telemetry to monitor the space astronauts, but now they use it in every hospital. Fabrics, different ways of preserving food. I mean, it just goes on and on. So they're at the cutting edge. Maybe they're looking at it from a different perspective, but in our everyday life, now we're using those products that they develop. So there is a benefit.
Thank you. Sharon, did you want to add something? I saw you're unmuted.
I'm a little curious. We mentioned Venus a short time ago. I didn't really get into it. You say that the atmosphere is too full of CO2. Did I understand that correctly?
That's correct, yeah.
Well, why don't we go there to see what happened? Because it sounds like it's a dead planet. Why aren't we going there to find out what happened to it so we can know how to protect ourselves?
You're absolutely right. And there is a strong group of planetary scientists who are advocating and trying to push NASA exactly to do that. So I think very soon, with time and some more scientific and political motivation, we will have a mission to Venus and we will answer those questions that you ask so perfectly.
As badly as we want to go to Mars, I think we need to protect here as well as explore other places to take our.
But even going to Mars and looking at why Mars is not currently habitable is also a way that we're learning about how we remain habitable too. So the same kind of question that you posed for Venus still remains true on Mars as well.
Okay, thank you.
Mm-hmm. Sure.
All right, thank you very much. Stan, did you have a question? I see you're unmuted, but it could be from before.
No, I'm just sitting and listening.
Okay. All right, thank you so much, Dr. Shkolnik. I really appreciate it, and I know everyone else did. Again, I wanted to, before I just hang up or officially close, I wanted to just remind you, everyone, next week, we're moving to 3 times a week and possibly The 4th and 5th days might be just informal social, coffee or something. But 3 official days. So next week we have on Monday Alex Picker is his name. He is a Jewish member of the, I guess, Mexico City community, is talking about an experience that he had and his faith involved. He was in another plane accident, different than our pilot of Flagstaff, because we did have Clark on Monday.
I know Clark. Oh, yes.
Yeah. So we had him on Monday. This Monday is another person who will share his story. Wednesday, we have a financial advisor from Harmony. And on Friday, we'll have actually someone doing some tunes, music, Scott Leader, a local recording studio artist in town. So again, look out for that email. I do want to thank you again. It was very informative and I appreciate it. I know everyone else did.
My pleasure. Thanks for asking.
Thank you.
Shabbat shalom, everyone.